Okay, IB11s, let's continue 4C, laws of logarithms, the second part. In the first part of 4C, we have already introduced 4 laws of logarithms. Those 4 laws are product law, quotient law, power law, and the root law. So right now, in this section, we will apply all those 4 laws to solve log equations. Let's look at the first example. Write these expressions as logarithmic equations in base 10. So they require you to use the common base to change every equation to the logarithmic equation. Let's look at the first one, y equals a squared b. If these two sides are equal, then I log both sides. So this process is called log both sides, which means I put the log for both of these two sides, and they are still equal. With the log laws, log a squared times b can be turned into log a squared plus log b, because this is the multiplication. The product law can help me split the multiplication into the adding of 2 logs. And this 2 is in the exponent. So I can use the power law to bring this 2 to the front of the log. So my final logarithmic equation is log y equals 2 log a plus log b. So that's how I can change any regular equation to the logarithmic equation. I hope that you guys can have a try, B, and see yourself. So you can pause here for a little bit of while and then come back to check your answer with my answer. So the second one, y equals a over b cubed. I log both sides. On the right side, this is log a divided by b cubed. So this is the quotient. We should use the quotient law to split this log. So it's log a minus log b cubed. For b cubed, this one has the exponent. The exponent can go to the front of the log based on the power law. So the final result for the logarithmic equation, it should be log y equals log a minus 3 log b. How about the last one? So I log both sides. They are still equal. Then this is the quotient. I use the quotient law to split the log on the right side. So it's minus log the square root of n. And for the square root of n, it's the same as, so this is n to the power 1/2. I bring 1/2 to the front. So it's 1/2 log n. This one is log p. Okay, so right now, example 2, we need to work in another way. Write the following equations without logarithms. So in this case, we need to get rid of the logarithms in the log equation and change the log equation back to the regular equation without the logarithms. If I want to get rid of the logs, on this side, I only have one single log. This is perfect. So I keep a single log on the left side. But for the right side, if I want to get rid of the logs, at the end, I need to combine these 2 logs to 1 log. With the adding, if you want to combine these 2 logs to 1 log, you have to get rid of this 2 in front of the log. How can I get rid of the 2? I can use the power law backwards. I put this 2 back to the exponent for argument c. So I will have log b plus log c squared. Without the coefficients in both of these two logs, I can use the product law to combine these two logs into one log. So for adding, and they have the same basis, I only need to multiply the arguments. So log a equals log b times c squared. Right now I have two logs on both sides, and both of these two logs have the same base 10. Like the exponential equations, if I can change both sides of an exponential equation to the common base, then I can ignore the base and just make the exponents equal. So logarithm equations are the same. If I have two logs on both sides and they have the same base, then I can ignore the log symbol with its base as well. So then I will have a equals b times c squared. So that's how we can cancel the logarithm symbol in an logarithm equation and change the logarithm equation to a regular equation. Can you try this one yourself? Here in b, if you want to change the right side to one log, you need to change number 2 to a log with the same base 2. Of course, on the left side, in the log, the base is 2. On the right side, there's another log, the base is 2. So that means I need to change this constant, number 2, to a base 2 log as well. How can I change any constant to a log? It's very easy. What I will do is, I change this number 2 to 2 times 1. And we have already talked about this one last time. For number 1, as long as base is the same as the argument, this log value is always 1. So log 2 is 1. Log 3 to the base 3 is 1. Log 4 to the base 4 is 1. Log b to the base b is also 1. So in this case, I always can change any constant to any base in the logarithm. So right now, for this case, of course, I will change number 2 to the base 2 log, which is 2 times 1, and change this number 1 to log 2 or 2. If I want to combine these two logs in the subtraction, we know this one already. We need to get rid of these two coefficients in front of the logarithms by using the power law backwards. So for the first 3, I put this 3 back to a, which is a cubed. For this number 2, I put this 2 back for number 2, which is 2 squared. So it's log 2m. Okay, right now log 2m equals log 2a cubed minus log 2 squared, which is log 4. Then I can use the quotient law to combine these two logs in the subtraction. So I keep one log, divide the arguments. So it's a cubed divided by 4. So right now I have one log on the left side and one log on the right side. And both of these two logs have the same base. I can ignore the log symbol as well as its base. So I will get m equals a cubed over 4. This knowledge is also the fundamental principle for us to solve log equations. So let's look at these two other facts for solving exponential equations and the log equations. If b to the power of f of x equals b to the power of g of x, so this one is an exponential equation. I change the left side to a base b power. And I change the right side to a base b power. And both of these two sides have the common base, which means I can ignore the base and make the exponents equal. Likewise, we have the same principle in the logarithmic equations. If I have one log on the left side, which is log b f of x, and the other log on the right side, log b g of x, and these two logs have the same basis. Of course, for the arguments, they have to be larger than 0. Because in logarithm, we are supposed to know this one already. For the exponential function y equals b to the power of x, its inverse is y equals log x in the base b. For any exponential function, we know its domain is all real numbers. And the range is y is always positive, is always larger than 0. As the logarithm is the inverse of the exponential function, we know the domain of the original function becomes the range of the logarithm inverse function. So the range here is y can be all real numbers. But my domain for the inverse is from the original range. So this x has to be greater than 0. So that means for any log functions, the argument x must be positive. This reason we see the restrictions here. Okay, with this restriction, and I have two logs on both sides, and these two logs have the common base, then I will know I can ignore the log as well as its base. That means the arguments in these two logs must be equal. So that's how we can solve the log equations. So let's use this principle to solve the following log equations. Number 8. I have log 3, x minus 1 equals log 3 to x minus 3. This log equation is so perfect already. I have one log on the left side, one log on the right side, and both of these two logs have the same basis. So I can ignore the log symbol as well as its base. That means x minus 1 equals 2x minus 3. So right now, this log equation becomes a simple linear equation. And I do believe most of you guys can solve this linear equation already. How can I solve this linear equation? I isolate x from the numbers. So I move 2x to the side and bring negative 1 to the other side. Become positive 1. So x take away 2x is negative x. Negative 3 plus 1 is negative 2. Then divide both sides by negative 1, x equals 2. For the log equations, make sure that you can check the solution at the end. It's mainly because for the log equation, we have the restriction, which means these two arguments must be positive values. With the solution x equals 2, can you check if this x equals 2 fits this log equation, which means this x equals 2 can make both of these two arguments positive. So you will see the left side is log 3, plug 2 in for x is 1. And the right side is also log 3, 1. The left side is equal to the right side. This one means x equals 2 fits the arguments and fits the log equation as well. So x equals 2 is the solution of this log equation. Okay, let's look at B. How can we solve for B? you have to combine these two logs on one side into one log. So this one is the same. I have to combine these two into one log as well. The left side is easy. And both of these two logs have the same base. With the adding in the middle, so that means I multiply the arguments. So it's x plus 14 times x plus 2. For 3, I need to change 3 to a log. And we talk about how we can change the constant to a log. I change 3 to 3 times 1. And make this 1 into log 2 with the same base. And then bring this 3 back to the exponent. So it's log base 2 cubed, which is 8. So this 3 actually is log 2 cubed. Then I combine these two logs by multiplying the arguments. So it's 8 times x plus 6. So right now, I have one log on the left side and one log on the right side, and they have the same base. Then I can ignore the log symbol with its base. I will have x plus 14 times x plus 2 equals 8 times x plus 2. So this is a regular quadratic equation. How can we solve this regular quadratic equation? I need to open the brackets and then bring all the terms to one side and leave one side to be 0. So let's open the brackets using the FOIL method here. It's x squared plus 2x plus 14x. Add the like terms up. It's 16x. Then plus 14 times 2, it's 28, equals 8x plus 48. Let's bring all the terms to the other side. So let's bring 8x and 48 to the left side. So it's x squared plus 8x plus 28 minus 48, that's minus 20, equals 0. Factorize this trinomial, we can get x minus 2 times x plus 10 equals 0. So from this quadratic equation, we will get two solutions. One is positive 2. The other x is negative 2. But are all those two solutions the solutions of this log equation? I don't know yet. So what I need to do is check which one is the solution, which one is not the solution. So when you check the solution, you need to put the solutions back to the very original equation. This is the initial one. So I put x equals 2 back to the initial one. So the left side equals log 2 plus 14, then plus log 2 plus 2, which is log 2 16 plus log 2 4. You can simplify this one into log 2 16 times 4, which is 64. So for log 2 64, you guys can find the value. This value is 6. Okay, let's look at the right side. So right side is 3 plus log 2 plus 6, which is 8. And we know log 2, 8 is 3. So 3 plus 3, it's really 6. So that means x equals 2 is the solution for the logarithmic equation as well. Okay, how about x equals negative 10? So x equals negative 10. I will do the same thing. So left side, I plug in. I will have log 2, it's negative 10 plus 14. Then plus log 2, negative 10 plus 2. Okay, I even don't need to continue anymore because I will see the problems arising. And this checking. This argument is a negative 8 value. So the argument is negative. It's not going to happen to the logarithm. So this one is undefined, which means x equals negative 10 cannot make the arguments positive. So x equals negative 10 is an extraneous root. Should be rejected. So this is a reject. So the final conclusion is the original equation only has one solution, which is x equals 2. Okay, so that's how we can solve the log equations. I'm not so sure if you guys can have a try yourself in C and D. Let's look at how we can solve for x in C. I need to combine these two logs to one log. So it's log with the minus in the middle. We know this one is the quotient law. So we need to divide the arguments when we combine the logs into one log. So I have this log equals this log, and both of them have the same base, which is a common base. So right now, I can ignore the log symbol and their bases. So it's x over x minus 1 equals 3. For me, I will take 3 as a 3 over 1. Then for this rational equation, I can use cross multiply. So x times 1 is x equals 3 times brackets x minus 1. Okay, when you cross multiply the top by this denominator, don't forget you need to use a pair of brackets for the entire denominator. So this one is 3 times brackets x minus 1. So open the brackets equals 3x minus 3. Let's look at the final solution is negative 2x equals negative 3. So x equals 3 over 2. After you solve a log an equation, you always need to check the solution to look at if x equals 3 over 2 is the solution for the initial log an equation. The left side is log 3 over 2 minus log 3 over 2 minus 1, which is 1/2. And I find that this 3 over 2 can make both of these two arguments positive. So that's the first step in the checking. And the second step is the left side. You can continue to simplify these two logs in the subtraction. You divide the arguments. It's log 3, which is the same as the right side. So far, I can make a conclusion. So x equals 3 over 2 is really the solution of the initial log equation. Okay, the last one. So the same idea as what we did in the first 3 log equations. First, we need to combine these two logs into one log. Minus in the middle, that means it's dividing for the argument. So it's log 2, 3 minus 2x over 2 minus x equals log 2, 3. Both of these two sides have the same base log. Ignore the log and its base. The arguments must be equal. A rational equation again. I'll make the 3 into 3 over 1. Then I can cross multiply. 1 times 3 minus 2x is 3 minus 2x. 3 should be multiplied by brackets 2 minus x. Don't forget to put on the pair of brackets for the denominator. So 3 times 2 is 6. Minus 3 times x is 3x. So isolate the x from the numbers. So it's negative 2x plus 3x equals 6 minus 3, which is x equals 3. Let's check the solution to look at if x equals 3 is the solution of this initial log and equation as well. Let's put down check. Okay, x equals 3. Let's plug x equals 3 into the left side. So my left side will become log 2. In the first pair of brackets, it's a 3 minus 2x. It's a 3 minus 6. Minus log 2, 2 minus 3 again. With the first step of the check, you will see, okay, both of these two arguments are not positives. So this one is negative 3. This one is negative 1. Okay, it's not going to happen in the logarithms. So this one is undefined, this one is also undefined. So that means x equals 3 cannot make the arguments in the initial log equation to be positive. Although I have only one solution, x equals 3. However, this only solution is an extraneous root, should be rejected as well. Okay, I really hope that you guys can do some homework to practice how to solve log equations.